Thank you very much for coming. The story about me breaking my finger is true, and it is true I was taking my wallet out of my back pocket. I honestly don't know how I did it. I was getting my wallet out and I heard my finger snap. And when it came out, it all flopped over and it hurt. But actually the most painful thing was the 6 weeks of jokes about the size and weight of my wallet while it all snapped up. So, of course, when all the posters are printed, you think of a slightly better title. And so the official title is Lies, Damn Lies, and Tricking the Light Fantastic. So my story starts with the optics I learnt at school, and I was told something about how light refracted. Even as a kid, I noticed that when you put a pencil into glass, that the pencil appears bent. And then when I was at school, I was told that something about the wavelength changing as it passes from one medium to the other, and the incidence and refracting angles are being connected in this way. We drew a simple diagram and then showed that this law was the relationship, where this quantity n is the speed of light in vacuum divided by the velocity of light in the medium. Now, there are records, I believe, in the 10th century of manuscripts that indicate some knowledge of this law, but there are many different discoverers, but one that with whom the name is principally associated is Willibrord Snellius in 1621, and hence it's called Snell's law. Now, I've spent quite a significant part of my career, I guess, trying to understand better what we mean by refractive index. And since we think that the speed of light in vacuum is a constant, essentially that boils down to understanding what I mean by the velocity of light in the medium. What velocity does it actually refer to? Is it the transport of something real and physical, or is it something else? Well, the first path towards that understanding derives from a very beautiful set of equations written down in 1862 by James Clerk Maxwell. He wrote a book, which I have here. It's not exactly bedtime reading, but he wrote down everything that was then known about the electric and magnetic fields. But like all great theories, and I think, in my opinion, Maxwell's theory is one of the great syntheses of physics. Like all great theories, it actually went one or two steps further than the domain of experience. So whilst it expressed everything that was then new about, for example, static electric and magnetic fields, Maxwell's theory is a dynamic theory and tells us, in particular, what happens when the electric and magnetic fields are dynamic and change with time. And in particular, the equations describe how changes in electric field E can generate a magnetic field B and vice versa. So this is really quite beautiful because it means that once a source has set off an electric and magnetic field in this way, it's a bit like sort of a butterfly flying off from a flower or something. The field can be self-sustaining because the changes in one field feed the other field and vice versa. And so we led to this remarkable and beautiful solution of Maxwell's equations that propagates what's called an electromagnetic wave. And the properties of this wave are derived from Maxwell's equation. So it has something called polarization, which means that the plane in which the electric and magnetic field are restricted to orthogonal or perpendicular planes travels at 300 million meters per second. And this is a quantity that actually comes out of the theory. So as Maxwell himself put it, we can scarcely avoid the conclusion that light consists in the transverse undulations of the same medium, which is the cause of electric and magnetic phenomena. And so the light that reaches our senses is essentially this electromagnetic wave. And so this is the picture in terms of how light travels in vacuum. If I'm going to understand something about how light slows down in materials, I need to look at the interaction between light and media. And now, I wasn't told this at school, but I learned this more as an undergraduate, that I understood that the electric field of the wave that is incident to some medium causes charges to oscillate. So it causes separation of charges, positive and negative, into a configuration that's called a dipole. And for a fixed value, for a fixed source strength, we can say that the charges separate by some distance, let's call it d. And then we can use this distance d as a measure of the strength of that interaction. So actually, if we put in some more constants, it becomes a dimensionless number, and then we give it a different symbol. We call it epsilon. Now, Maxwell's theory tells us how oscillating charges, oscillating dipoles, will then also radiate a new field. So there's a source field. It excites charges to dipole oscillations, which then radiate. And so the picture that emerges is this one, where the source field excites the dipoles, and we might want to measure the electric field at some point p away to the right. Now, the picture now, as I understand it, as opposed to simply saying that light slows down as it enters a material, is something like the following. That when we look at the electric field at some point p to the right, it's a combination of the source and the radiation bits. And when you add them together, it appears as though that resultant wave, that combined wave, is slightly retarded with respect to the source being, if you took this material away. And so the source comes along, it rattles the charges, it reaches some kind of steady state, and then we can measure it like so. Now, it's this retardation that is now pertaining, it's now what relates to the slowing down of light as it enters the material. We can summarize that then, that the total field appears to slow down by a factor of, actually it's the square root of this dimensionless number epsilon. We call it n, and we could give it a name, the refractive index. Now, a key point that I now appreciate a bit better than when I was at school is that electromagnetic energy may or may not actually be flowing at the same rate as determined by this slowing down. And so there's a distinction between a velocity that is a real transport of something, a real transport of energy or an object, or what we might say is a geometrical velocity. And I want to illustrate that point with a simple demonstration. If I take this card and put it on the visualizer, I take another card like so, I can push the card like this, and the point of intersection moves from left to right. I don't think I can keep both hands steady at the same time, but you can see what I mean, that the point of intersection moves to left to right. But that's purely a geometrical speed. I can make that speed anything I like, including faster than the vacuum speed of light, just by making that angle as small as I please. It just can zip off as fast as I please. What is the transport of something that is real and physical in this analogy is the arrow, which also proceeds from left to right. It represents the transport of something physical. I can make the analogy even more stark by actually tilting it the other way, so that when I push the card like this, the point of intersection moves backwards, but that's just a geometrical thing. It doesn't actually represent the movement of anything physical, whereas the arrow is still proceeding in the same direction as before. So this is, in this analogy, this geometrical point refers to, say, a geometrical velocity, and it's that kind of slowing down that the refractive index refers to. And we'll see this occurring again a bit later. Okay, so I'm interested, although it represents a geometrical slowing down, it's still interesting to explore how refractive index can vary. And in particular, I've been very interested over the years in how refractive index can vary with respect to position, with respect to the direction of the electric field, and with respect to time. And so I'm going to just give a few examples of those possibilities and how they've related to some work that I've done. The very simplest example, if we change the epsilon or the refractive index with position, is if you look out of a window, you see a reflection. Normally it's only a small fraction, about 4% for an air-glass interface. But we can make things a little more interesting by adding a second interface. And you've also seen this quite commonly in an oil film, where light is incident to the surface, is reflected, but then combines with another reflection from the back of the interface. And then depending on a condition that relates to whether these two contributions add up together or add up oppositely, we either see a dark fringe or a bright fringe. But this is a condition that is dependent on the wavelength, and that's why we see these colours in an oil film or puddle on the road or whatever. And so the reflection depends on wavelength and film thickness, and it gives us the idea that colour can actually occur through the structure of materials. That can be extended to lots and lots of interfaces, and so we could have a varying refractive index with different thicknesses, and if we design it carefully, we can actually get, although each individual reflection is quite weak, if we design it carefully, those reflections can add up together to give a very, very strong reflection, about almost 100%, very, very close to 100%. But as you add more and more layers, the reflection gets close to 100%, but it becomes a very, very precise wavelength that will do that. And so that's used quite widely, for example, in laser mirrors, where you want to have a very high reflectivity, and also in some of the advanced filters that are used in wavelength division multiplexing, so in the optical communications that supply the internet, for example. The basic point is that we can influence what the colours we see through the structure of the material. So we can change the refractive index with respect to position. My second example is one where we change the refractive index, or the epsilon, which is its square, with the direction of the field that's exciting. So in my simple diagram a few minutes ago, I had the electric field exciting these dipoles into oscillation, but it may happen that the excitation can be greater in the perpendicular direction and leads to a different value of that separation distance. It needn't be the case that the exciting field has the same medium response in one plane as it does in another. And this leads to the possibility that we can have two refraction indices associated with the direction. And again, I'd like to show that possibility with this crystal. So this is a crystal, it's called calcite. It has this property that the dipoles that are excited have different strength in one direction than the other, and so it has two refractive indices, and we perceive that as two different images. As suggested by the diagram, they are indeed in perpendicular directions, and I can demonstrate that by placing the Polaroid foil over the top, and you can see I can alternate between the one image and the other like so. And interestingly, this is kind of an example of what I was talking about a few minutes ago with respect to the geometric speed that is associated with refractive index and the actual flow of electromagnetic energy. Because actually, the planes of oscillations for both of these images are roughly parallel. But the direction of electromagnetic energy flow is slightly different for the two images. And so that points up this aspect that what we perceive in our senses is through the flow of electromagnetic energy, which may or may not be the same as this quantity which we call it relates to this quantity that we call refractive index. Well, I've been doing some work over the last few years in which these ideas have actually been combined. So the idea of a variation with respect to position and a variation with respect to direction can be combined. And so we can take a crystal, such as my calcite, but deposit it in very thin layers. So we have a source that can evaporate. It's generally done upwards, actually, and evaporates onto some kind of substrate. But we do it under very careful vacuum conditions so that we can deposit a very thin layer, rotate the substrate just a little bit, and then deposit another layer. And so you can see that layer by layer we can build up a twisting or helical structure that combines the two features of refractive index varying with position and varying with direction. So there are these two special directions that carry different refractive indices, and so they're in two perpendicular directions, but those two directions can actually be varied as we move through the through this structure. So we build up a helical or handed type of film, and these are the kinds of structures, they're quite beautiful really, that can be made by different types of substrate rotation. We can do Z shapes or swirls and S's. I've been particularly interested in this helical structure, which we have just here. Now, when we're dealing with a helical structure like this, whereas I said at the beginning that the electric field vibrates up and down or side to side, an equally valid description of the electric field is that it's circularly polarized, so it can either be circulating to the right or to the left. Now, for these helical structures that I've been interested in, it's more natural to choose this helical arrangement. So what happens when light is incident to one of these helical structures? They're handed, so they pick up or are sensitive to the circular polarization. So when light is incident to such a structure, in this case a lot of left circular polarization is reflected. If you get the wavelength exactly right, I'll explain what I mean in just a second. And the right-handed component is transmitted. As Joe was saying at the beginning, I collaborate with Ian Hodgkinson in Otago in Dunedin, where I did do some other things other than dance the rock, but we worked on looking at analysing the spectra that come from these samples. And so what's illustrated here is that you get a strong reflection in the left-handed. So these are actually in transmission. So when a strong reflection translates to a small transmission. And so if you get the wavelength exactly right, you get a minimum in this spectrum, whereas the right-handed is pretty much transmitted flat. This is theory and simulation. Now I want to explain a bit more carefully how that works. I've got my model here. This is a helix. Now I've brought along this isn't a magic wand. I'm not going to make you all invisible. Not yet, anyway. And actually this represents the electric field. So remember, the electric field is circularly polarized. So I'm not very good at baton twirling, but you can imagine it sort of going round and round like this. Now, this helix represents the chiral or handed thin film structure that I have there. Now, if I have a circular polarization that is the same sense as the helix, can you see it sort of rides nicely along the surface of that helix? Actually, it sees some kind of average, whereas at some kind of average refractive index. Whereas if it's rotating contra to the helix, it sort of always cuts into the surface. Right? So whereas if I go a couple of slides back, you can see I'll find my presenter. Oh yeah, here it is. If I go back to that situation I had a few moments ago, you can see that we have N1 and N2 in this helical arrangement. When we have the electric field contra, it sort of continuously cuts in. So at one point it sees N1, and then it sees N2, and then it sees N1 again. It's exactly the alternation that you get in a standard thin film structure, like I showed you a few slides back. But notice in this case that it's specific to the polarization. It's only, in this case, the left-handed polarization that sees that variation. The other hand doesn't. And so we get quite a nice possibility of introducing into our filters, our mirrors, and our devices, the idea that that filtering can be polarization specific. And so this has applications in communications and sensing. And in fact, there's a company called Chiral Photonics that actually embeds these chiral structures into optical fibers. And the thought there is that we can utilize this polarization discrimination to actually increase the bandwidth of systems. So I've spoken so far about the electrical response, the response of a medium to light's electric field. I've said very, very little about the magnetic field. Oh, sorry, before I get on to that, just to mention something else. So we can make these chiral coatings. They're made of titanium oxide and many other substances. And they can be, so they appear different colors, and they can be, according to what hand of filter we present them, they can either be dark or bright, according to whether we present left or right circular polarization. Now, that's all fine. We also understood more recently that these structures also occur in nature. Now, nature doesn't have a vacuum deposition system designed to actually make these helical structures, but it has got the advantage of a few million years of evolution, and they are found in some species, in this case Manuka beetles. And I have an example of a beetle that does have this property that I just want to show you. Let's see if I can zoom that in a little bit. My former bosses at GC will testify that I'm experimentally incompetent, so there we go. So this is what I claim to be a beetle that has this circular polarization discrimination. I can sort of show it to you by putting this filter over. You see, as I rotate the filter for the calcite image is discriminated. In this case, it gets darker, but it pretty much remains the green colour. Now, if I don these natty spectacles, you may recognise these from going to watch 3D movies, although personally I've never been to see one myself, but I'm told that this is what you get when you go to see one. You see the 3D-ness because the eye is presented with different images through the polarization discrimination. What's less well known is that these are actually circular Polaroids rather than linear polarizers. They discriminate between left and right circular. And the reason for that is so that you can tilt your head whilst watching the movie and you can still see the 3D-ness. Anyway, that's by the by. If I put these over the beetle, you can see it remains green for this image, but for the other one, it goes black. And so that indicates that it is indeed a circular, has a helical structure. We don't know why. I've got myself and Kenny Weir have a couple of students at the Department of Entomology that are going through racks. You wouldn't believe what you can find behind the scenes at the Natural History Museum, but there are racks and racks and racks and racks of these beetles. And the students have this sort of unenviable and rather sort of Kafkaesque task of just sort of wading their way through it. They've never come across a right-handed one. They seem to be almost invariably left-handed. We don't know if it's to do with the visual system in terms of attracting mates or whatever. As far, there are other insects that have recently been discovered to have this circular polarization discrimination, but we don't know for this particular species. It may be just an evolutionary accident that the chiral exoskeleton gives extra sort of structural support. We just don't know. Okay, so now back to what I was going to say about the magnetic field. Everything I've said so far has related to the electrical response of the material, and normally as undergraduates we're not really introduced to the magnetic response of materials. It's considered dull and uninteresting, but in fact it's not dull, and it is very interesting, believe me. But we just don't normally encounter it in normal situations. But just to review how it works, we have the magnetic field. And we actually have a very, very similar picture to what we had at the beginning with the electric field. Again, now it's the magnetic, the B field associated with some light source. Again, it does something to the medium, and the result is a combination of the source and radiation. And again, it appears slightly lagged with respect to the source on its own. Now, there isn't some physical distance that you can associate with what the light does to the medium in this case. In this case, you have to, you can assign the strength to the size of little currents that are set up in the material. And again, by throwing in some other numbers, we can make a dimensionless quantity, which we now call mu, Greek letter for M, so M for magnetic. And so the picture is somewhat similar, and the conclusions are similar, that the total field appears to slow down, this time by the square root of the mu number, and again we call it the refractive index. And again, the conclusion applies that electromagnetic energy may or may not be flowing at the same rate. So to review, we have, I've learnt quite a lot now about refractive index in electromagnetic media. I understand it's to do with, firstly, with respect to an electrical response, the response of a medium to its electric field, and similarly with respect to a magnetic field. The velocity of light in the medium, as I was told at school, is the velocity of light in vacuum divided by n, where n is the refractive index, which is now given by, if you include both the electrical and the magnetic parts, is given by the square root of epsilon and mu together. Now, the fact that this is a square root suggests that something interesting might happen if either or both of these quantities were negative, because then we'd have an imaginary refractive index, and that might be quite interesting. In fact, you encounter, it's very easy to make the electric field bit, the epsilon, negative. It occurs very easily in metals. So free electrons in a metal, the electrons form a plasma, and if you excite that with an electric field, then beneath what's called the plasma frequency, the electrical response, and we're just interested in this bit, the real part of epsilon, dips below the axis and becomes negative. So it's quite easy to make the epsilon negative, and then they would have an imaginary refractive index. So what does that actually do? What happens when an electromagnetic wave tries to travel in such a medium? Well, you see this every day when you look into a mirror, because actually, as the wave tries to penetrate it, it finds that it can't. And actually, the wave that approaches the metal or the mirror, it decays quite rapidly, can't penetrate. There's no travelling wave that can go into the material, and since the energy is conserved, it's radiated backwards. In fact, you can also think of it in terms of the electrons shaking up and down and radiating backwards. And so that's essentially what you see with a mirror. But what happens if both the electrical response and the magnetic response are simultaneously negative? That's quite an interesting question, a very interesting question. This was addressed by Victor Veselago in 1968 when I was just a kid. And I have to talk fast because my simulation is running. You can see what happens is that if both these quantities are negative, we have a really stark situation where the electromagnetic energy flows in one direction, whereas the wave oscillations travel in exactly the opposite direction. So really pointing up this idea of the difference between what I call a geometrical speed and a real physical transport of energy. You see the envelope, I started with an envelope consisting of a few cycles of radiation. It's now it starts off in a normal material or vacuum, whatever, and then encounters this material which has this kind of double negative property, that the electrical response and the magnetic response are simultaneously negative. Now, see what happens. It's the energy is associated with the envelope of this structure, but notice that the oscillations are actually travelling backwards. So the oscillation is going backwards whilst the energy is travelling forward, and indeed is emerging from the other side of the material. This was a purely theoretical pursuit by Veselago, but this is an accurate simulation of solving Maxwell's equations. So this is what we believe would happen. And so in terms of my pursuit of trying to understand refractive index and so forth, this is properly described by a negative refractive index. Remember, it is the speed of light divided by the speed of light in the medium. And so the oscillations in this case are travelling backwards, and it's appropriate then to assign this a negative quantity. So we have this kind of diagram that summarises where we are. We have two axes, the electrical response, epsilon, the magnetic response, mu, and we've normally these quantities are positive, and that's what we know from most materials. Can be negative if the electrical response is negative. We encounter that also commonly with metals. Just a negative magnetic response doesn't occur naturally, but would behave in a similar way in terms of this decaying, with the electromagnetic wave being unable to penetrate. And the double negative region that I've just described, which contains this backward wave. So it's quite interesting that what would actually happen for light that's refracted in such a material. This isn't a photograph, but Ortwin Hess has kindly let me use this picture, which shows what would happen is that if you put a straw into the negatively refracting water, it would bend backwards. I'm just going to take a sip of ordinary water because my throat's getting a bit dry. Now, is this actually useful for anything? Are there any applications? It might be a good party trick to put your straw in and it goes the wrong way or whatever. But there's some very interesting work done by John Pendry. Where's John sitting? Oh, there we are. I won't flash the laser at you. in the year 2000 that showed that there is a very important consequence of this negative refraction. And that is, if you take a slab of this double negative material, the first thing is it images in quite an interesting way. You can just draw rays. They refract negatively at each boundary like this. And you get a near-field imaging. So you have an object and an image. It's not the 1 upon u plus 1 upon v equals 1 upon f formula that I learnt at school. It's rather that the sum of the object distance and the image distance, d1 and d2, has to equal the layer thickness. So it's a flat slab of this material automatically forms a lens, and that's quite interesting. But as John showed, there's a more important and remarkable consequence, and that is that there are aspects to the field, the electromagnetic field, that are not travelling waves, but rather waves that decay away from a source. And the remarkable feature of this double negative material is that these waves that are decaying actually become amplified and then decay the other side of the material. And it works out beautifully that once this process has occurred, the height at the image is exactly the same height as at the object. Now, these decaying waves are associated with information that is normally lost in conventional imaging. So in a conventional lens, the resolution or the detail that we can see is limited by the wavelength of light. But these decaying fields that carry this very detailed information in this type of lens are actually restored. And it appears as though there's no in-principle limit to the resolution. And so it's been coined the name perfect lens, in the sense that we believe that our ability to see the finest details is now limited by technology rather than the wavelength of light. And this was shown in some experiments from Berkeley that with an imprint of the word nano. It's not, actually didn't use a double negative material, it used a single negative material, which is a silver slab, but it inherits some of the properties that that I've talked about, and you can see that there is an improvement in the resolution. How can we get a negative magnetic response? It's hard. It doesn't occur naturally. It's difficult, and the graph there shows a possible way forward in terms of exploiting the fact that Maxwell's theory is a dynamic theory. The fact that forces and responses are not always what you think intuitively when we think of things dynamically. So we're used to the idea that a force and a response, say this mass, will go in the same direction. So if I push on something, it will travel in the same direction. And that's true if I take the mass and I just gently force it up and down. But if I do it a tiny bit more quickly, so I go through the resonance, you can see that actually the mass is moving opposite to the direction of the force provided by my hand. And so this is a characteristic of resonance systems, that as you go through a resonance, the response becomes, as we say, in antiphase with respect to the driving force. So the response becomes negative with respect to the driving force. So can we utilize that in terms of trying to access this negative magnetic region? So it doesn't happen in, so this is the response curve is a small negative region. It doesn't happen in natural media, but there is big growth in the field of metamaterials, where we believe we can influence the magnetic properties through very tiny metallic structures that are infiltrated into the material. So these are sub-wavelengths, so that we have what called split ring resonators. These are little tiny inclusions, so that they engage a magnetic field that sets up a circulation of current. They're resonant because of they're split and they're capacitive, so there's a capacitive resonance, and then just above that resonance, the magnetic response can be negative. So it's artificially induced. So it's this, if you like, function through structure rather than through the chemistry of materials. And so this was done in the early 2000s. A negative index metamaterial consisting of these split ring resonators and vertical columns of wire, respectively engaging the magnetic field and the electric field. So the wire bits give us the negative electrical response, a bit like the mirror, and the split ring resonators give the magnetic response. It's all set up at microwaves, but it demonstrated the right properties. This is actually a more careful designed experiment. So it has a prism made out of this double negative metamaterial, and it refracts the wrong way as compared with a conventional prism, in this case made out of Teflon. So this all works in the microwave, but subsequently we've been able to push that much more towards optical frequencies. Now, when we get a really new piece of physics like this, it's interesting to explore and exploit it in various ways. And people like to look at different contexts, see whether these ideas can be applied in different ways. And one way that was popular in the about 2005 was to examine the possibility whether gravity could induce this negative refracting property. It's not a silly idea, not very silly anyway. But these gravity can curve light, and these beautiful images of gravitational lensing, you can see circular structure is actually due to a point source behind some gravitating object. And by analogy, you can refract light in materials for which the refractive index is varying with position. In this sugar solution, for example, the density increases with height and it curves the light in this way. And this is the basis of how a mirage works. And there's a correspondence, therefore, between the curving of light in vacuum, as in gravity, and with materials. And that correspondence can be made exact. It's not just a sort of vague analogy. The correspondence can be made exact. For a given gravitational configuration, you can find a corresponding material that has the same electromagnetic, whose electromagnetic properties will produce that same curving. Now this caused quite a hoo-ha because it was suggested that in the ergosphere of black holes it would be possible to negatively refract, and there were specific claims that this could be done. The idea was fundamentally flawed. Gravity is the curvature of space and time. And this analogy, which is quite a good analogy, I think, shows what happens for gravity. Gravity, if you take a sheet which represents the space-time manifold, and you can distort it like a trampoline, you have put a ball in the middle or something, you draw parallel lines onto a sheet. And those parallel lines don't remain parallel once you introduce this curvy bit. In fact, that's how you measure curvature. It's the relative acceleration of parallel lines. Now, it turned out that the proponents of the theory that said that gravity could negatively refract had made a mistake, and that they'd associated shearing type distortions with gravitational effects. So in fact, if you shear a surface, parallel lines still remain parallel. And so there was no a mechanism to produce these effects. The light gets its marching orders locally in both space and time. And locally, space-time is inertial and flat. There simply isn't a mechanism for it to work. But so how do you reach an incorrect conclusion? Well, what happened was that if you draw a simple diagram that shows space on this axis and time on this axis, then light occupies a straight line like this. Now you could, if you wish, invent a new axis called x prime that's some combination of space and time. It would be equivalent to measuring distance with a combination of rods and clocks, which is a pretty silly thing to do, but it would work. Now if you apply this, if you could use this new coordinate system together with the t-axis, I suppose. Now if you can make this shearing severe enough, it can actually cross the light line. Now in the context of the calculations as they were done at that time, they just use this effective medium approach, this analogy between gravity and a medium, and you lose sight of some of the mathematics in such a way that if this axis crosses the light line, you can convince yourself that a wave is moving backwards. But of course it's just a coordinate change, and coordinates shouldn't matter. And so that was the basis of that mistake. I'm afraid I got crossed off quite a few Christmas card lists as a result of work that I did on that area, but there we are. So coordinates don't matter. Well, actually they do matter if you ask the right question. This is about the most complicated slide I've got, so just bear with it for a second. Coordinates matter if you ask the right questions. I haven't actually written them up yet, but these in fact are Maxwell's equations in the way that we teach to undergraduates. And the form of Maxwell's equations must stay the same as we move from one coordinate system to another. And so what that means is if I invent, so for the plane x and y, I can invent some new x prime and y prime, everything's distorted, but the physics, which I represent by this blue arrow, the physics has to stay the same. Now, completely equivalent is my choice what to do, so a completely equivalent thing to do is for me to decide that I'm going to have my x prime and y prime on a rectilinear system, but to compensate, the physics, which of course in this case represents the electromagnetic field, has to wiggle just on the representation of this particular piece of paper. So that's not very interesting. That's the two ways that you can view a coordinate change can be either, as we say, active or passive. But there is a very interesting piece of information that we can get out of is studying how the piece of physics changes from one representation to the other. And that is how Maxwell's equations behave. We can ask the following question, and that is there a material that we can design that will actually produce this wiggling in a real physical material? And the point is that the invariance, the fact that Maxwell's equations have to take the same form in both systems, itself provides sufficient information to answer the question, what would the material have to look like in order for the field to wiggle in this way? So, I mean, the details are irrelevant, but we can see that that if we could devise some complicated epsilon and mu, which are functions of position, then we could actualize this this wiggling. And so that's the theory behind the so-called electromagnetic cloak, which was proposed independently by John Pendry and Ulf Leonhardt in 2006. And it's a beautiful idea in that so we could take a kind of coordinate transformation that does this is one that, so is one like this, a radial transformation. So if you set r in the original system equal to 0, you see that it punches a hole, a red blob in the middle of my xy axes. So what were originally straight lines then have to be curved in the new coordinate system to go round. But the invariance of Maxwell's equations tells us precisely what kind of material we would need to actualize this curving of the ray trajectories. It's a complicated material for which the electric and magnetic response is a complicated function of radius and other coordinates. And it's a significant and severe challenge to make it, but that's what was done in 2006 using this metamaterial design, and it sort of worked. So this is the theoretical calculation. of how an electromagnetic cloak works. It cloaks an object, object the size and shape of about a 10p piece. It's all in a microwave and wave-guided experiment. So this is the ideal situation, the wave fronts going around the object and being restored like this. And here's the experiment. It couldn't be done perfectly, so there were certain things that one had to compromise over. And you can see that it doesn't reproduce the theory exactly, but does show evidence of shadowing. But as compared, say, with the situation where there was no cloak present, the shadowing is much more severe here. So there's clear evidence that some form of electromagnetic cloak is possible. And in fact, some of you may have heard in the news a couple of weeks ago, another improvement on this design was based on a crystal like this, calcite. So my group, over the last year or so, has looked at a different kind of cloak. The cloak we just had cloaks objects. I've been interested in the possibility of cloaking events. The idea in a cartoon fashion is that you could have some safe with a surveillance camera and you could somehow edit out a piece of that safe's history. There's perhaps a bit where a robber ran in, stole the cash and made off. So the surveillance camera would just see the safe closed all the time. In the parliamentary parlance, it's a bit like sort of redacting a piece of history and taking it away. And so this is the idea of a history editor or space-time cloak that my group has studied. And conceptually, it's very, very close to the object cloak. In fact, the diagram is rather similar. Now we have axes in space and time rather than space and space. And because the light in vacuum, for example, clocks off equal distances in equal times, we'd expect to see, before we did anything, we'd expect to see blue lines that say along the diagonal like so. But we applied the same principles of these sort of coordinate transformation ideas and wondered what happens if we have a transformation that takes out a hole, this time at the center of space-time rather than two-dimensional space. And the effect of that would be to edit out certain events from history. So an observer off to the right here would always see a uniform light intensity. But the light in these sections, which are with respect to space, but at different times, the light would sort of break up into two mountains and a valley. And at this point, the event in the middle is not illuminated at all. So providing the safecracker doesn't strike a match and reveal himself, he can actually sneak in and do some deed, because afterwards the light is patched up and the observer off to sufficiently far to the right never actually sees what's going on. There are some minor details that might worry some of you, like some rays are required to go faster than the vacuum speed of light, and indeed in a severe case they're actually required to point backwards in time. But these were, details that you needn't be too concerned about. To get our heads around what's happening, it's kind of hard to visualize what I mean by light curving in space and time. And what it actually means is regulating the speed of light, both in regulating the local speed of light in space and time. And so this is a rather nice cartoon that my postdoc devised. And it shows that we're running alongside the cars, and these are the cones. And when the space-time cloak operates, a bit in the front, the cars here speed up, and these ones slow down just enough time for the chicken to cross the road. So that's what that's doing. So just to go back one second. So it's interesting to ask what happens a bit further downstream. Further downstream, we just see a steady stream of cars. So in terms of our chicken crossing the road, what we'd actually see downstream is the chicken instantaneously relocating from one place to another. So it creates a kind of illusion, if you like, of a Star Trek transporter. But this is actually a more careful calculation and addresses some of these concerns about faster than the vacuum speed, because this is and past pointing light rays. This actually overcomes those difficulties by a more careful design of space-time cloak. And the time slices here indicate a very clear minimum at that midpoint. Can you actualize this in practice? Well, just as in the case of a spatial cloak, the mathematics gives us the precise design. But just as in the case of a spatial cloak, there are aspects that we can't access with current technology, and so we have to try and design a poor man's version. Now, I won't go through the details of this, but we believe it's just within the reach of current fiber technology to do a kind of poor man's space-time cloak, in which using nonlinearity and optical fibers, you need several kilometers because the light travels so fast. But with careful design and control, we believe it's possible to cloak a few nanoseconds. Now, of course, that's not especially interesting macroscopic time scale that's of interest to us. But it is of interest, we think, in terms of processing and signal analysis. And so this is the kind of application that we have in mind, where you might have some processing conflict, in which a primary computation, clock signal or something, can't be interrupted, and yet an occasional priority bits run along a different channel, and these have to be processed. And so the conflict can be resolved by using a space-time cloak, because you could open up a gap in this primary computation, have your way with the occasional priority bits, and then seamlessly close up the primary computation. So as far as the external circuit is concerned, nothing would have been disturbed. Well, this was reported in the most prestigious academic journals. Actually, I was pretty pleased. Well, I regard it as the pinnacle of my career that I made page 33 of The Sun. But interestingly, the few sentences here were actually quite well constructed, I thought. I thought that was pretty fair. It's a bit unfortunate that it was juxtaposed to this headline. And in fact, in my opinion, these few sentences were better than the Daily Telegraph, which started off with "Beam me up, Scotty." And there was another report that apparently I'd made time travel possible. What I particularly liked about this one was the imaginative use of quotation marks. My local paper had a piece on it. The online version described me as a devout Catholic, and then the printed version had that word deleted, which is possibly closer to the truth, I don't know. But this is the only time my research has been of attention to the media, and it was very interesting for me to find out. First of all, the communications office here did an absolutely fantastic job in getting myself and my colleagues through the morass of media attention. But it did strike me that it is really important for us as scientists that our message is reported coherently and confidently in all kinds of areas, that our voice is heard well, because otherwise it's left to opinion formers and bloggers and things. And in many aspects, climate change and so forth, it's really important for us to get it right. So it remains then for me to wind up, and so I'm just going to wind up with the most modern expression of Maxwell's equations, not the form that we show them to undergraduates in, but an advanced form that actually emphasizes some of the underlying geometry. Maxwell's equations become almost forced as a consequence of the wiring of space and time once certain theorems are recognized. And this style of notation emphasizes that. So it's very nice to write things down in a compact notation, particularly if you're going to have them tattooed onto your wrist. That's upside down, isn't it? Oh, well, you get the idea. There we are. Actually, the mathematics that employs this form, although it's only been in the last few decades that this style of mathematics has been emphasized and has given rise to some of the discoveries that I've discussed today, the actual mathematics is very old and dates back to a book by Hermann Grassmann in 1861, 1 year before Maxwell wrote down the equations. So it has a very venerable history. It's the mathematics of exterior forms. His work was completely ignored at the time and went for several decades. He wrote rather despairingly in the preface, in a way that I think is actually quite an appropriate way to finish my lecture. And he said that even if this work should again remain unused for many years, there will come a time when it will rise anew, for truth is eternal and divine, and no phase in the development of truth can pass on without leaving a trace. Truth remains, even though the garments in which poor mortals clothe it may fall to dust. So I'd like to thank my people I've worked with over the years, my students and colleagues, both past and present. I'd like to mention particularly my current group, Paul Kinsler and Alberto Favaro, who've been very stimulating and enriched some of the ideas in a very beneficial way. Finally, I'd like to dedicate this lecture to my father, who sadly didn't live to see me get a chair. He took a very strong interest in my career and in the career of all his children, and I think he would have been very proud. Thank you.